Now, another part of beam design that we have to consider is shear design. And in this situation, we want our nominal factored shear resistance to be greater than or equal to our factored shear. The factored load of shear through the cross-section of the beam. Now again, we're going to have this cross-section that we saw previously, and this cross-section has not only the tensile steel in it, but it also has this rectangular hoop or stirrup of steel. And in this particular example, I have drawn an arrow pointing to that stirrup, and I've indicated that it is a number 3 bar, and that at every 6 inches on center we would have one of these rectangular stirrups in the cross section of the beam. That reinforcement will assist in the resistance to shear forces that exist in the cross section of this reinforced concrete beam. And so in this situation, of course, our task is to calculate phi Vn and make sure that it is greater than or equal to V sub u. In this case, phi Vn can be calculated as phi V sub c plus phi V sub s. And so you can see that there is a contribution to this nominal factored shear resistance from the concrete. There's a resistance provided by the concrete, and then there is also a resistance provided by the stirrups that are provided in the cross section of the beam. To calculate phi Vc, the easiest formula that is common to use, and this one is the one that I recommend, is phi times 2 times the square root of f sub c prime times b times d. And that gives you the shear resistance provided by the concrete itself. The other portion of the resistance is provided by any reinforcement that you have in the cross section, and it is equal to phi times the total area of shear reinforcement times the yield strength of that shear reinforcement times d over the spacing of the shear reinforcement. Now, for the case of shear, phi is 0.75, and as an example, in our case, we had number 3s at 6, and so a number 3 bar has a 0.11 cross-sectional area, that's in square inches. And you'll notice here that we actually have 2 such bars in this rectangle that is our tie. And those 2 vertical bars each have a cross-sectional area of 0.11 because it's made out of a continuous number 3 bar. Those areas then need to be used to calculate the total value for A sub V. So you see 2 times 0.11 because we have 2 number 3 bars that are vertical in this stirrup. We also have the spacing, which is S. In our case, it was 6 inches for this example that we see here. Now, this again is just an introductory discussion of shear design, so there are many other things to be said about this. However, this is the basic idea of how you calculate phi Vn, and then you would compare it to V sub u. There are additional things in the code. There are some rules about spacing and minimum stirrups, and you can look in these code sections here to find that information. Now, overall, when you are designing a beam, one of the challenges is deciding how big the beam is, how much steel reinforcement that you need, and that can be a little bit of a difficulty because, as I mentioned at the beginning of our presentation, these beams are custom made. So you get to decide how big your beam is. Now, there are some ways to estimate some of these dimensions for your beam or the amount of area of steel that you need. And so I have some rules of thumb that kind of get you started, and then you can check out phi mn greater than or equal to m sub u. You can also check out phi vn greater than or equal to v sub u. And if those things are true and it looks like it's efficient, then you're good. If not, you can adjust these estimates that I have here and then make your beam work the way it's supposed to. In any case, if you wanted to estimate the amount of steel that you need, you can calculate that by this ratio, m sub u over 4 times d. Now, this formula has been derived, and the units are supposed to be in a special form. So for m sub u, you're going to use units of kip feet, and for d, you're going to use units of inches. Now, this of course assumes that you have d already. That may or may not be true, but if you do have it, this would provide a way for you to calculate the total tensile steel, at least to get an estimate for that. And it turns out that this formula works quite well, so that's good. Now, the other thing is you might want to know the width of the beam that you should use. And so if you do have D, or you have just guessed a value of D perhaps, you could then calculate what B would be, or an approximate value, and that would be 20 times m sub u over d squared, again using these units that I mentioned before. Another kind of rule of thumb that kind of works for B is that it is approximately a good number to use is about half of H. You will tend to get some fairly efficient beam sizes by doing that type of thing. Another thing that people sometimes do to estimate this dimension H is to say that if you have a certain beam span, just multiply it by 3/4 of an inch. So if you had 20 feet, you would multiply 20 times 3/4 of an inch, and you would get H in inches out of this formula. Now, that's just an estimate. It's something that people have learned over time, tends to be a good way to get started, and so hopefully that will be useful to you. The other thing is that D then can be calculated from H as H minus 2.5 inches. Now, this is my own suggestion here. This number 2.5 will not always be the correct number, but it will at least get you in the ballpark for what the D value should be. This 2.5 inch value comes about from the fact that you do have to have a certain amount of clear cover. You have to have a little bit of room for the stirrups, and then you have to get to the center of that area of steel at the bottom of the beam. And so when you take all of those things into account, the total height minus about 2.5 inches is going to give you D approximately most of the time. That will be a decent value. And of course, when you learn more about reinforced concrete and the code requirements, you'll be able to verify this exactly according to code rules. The last item I have here is that the code does actually have some rules about the minimum depth of a beam. And so this can be seen in the code table 9.3.1.1. And these are minimum beam depths that the code prescribes so that oftentimes a person will be able to avoid having to do deflection calculations if they adhere to these minimum beam depths. Now, the next thing that I want to show you about beam design is that I have created a computer program that will calculate phi mn for you. And this is called the nominal moment calculator, and it provides some calculated output over here and results. It also shows a picture of the beam cross section, and it shows the portion that's in compression. It shows the total area of steel down here as a single bar. Even though there may be multiple bars, it just uses a single circle for the tensile steel. And this program then, after you provide it with input, it will calculate phi mn for you. I will in another video show you how to use this more, but suffice to say that that is something that will be beneficial to you and you can take advantage of. Here are a few final comments on beam design. I mentioned some of these previously. Beams can have multiple layers of steel in the tension zone. Beams can have steel in the compression zone also. And lastly, beams cast monolithically with slabs have flanges in the compression zone. You will perhaps understand this more when I go over the use of the nominal moment calculator computer program, because it has the ability to include flanges in the compression zone of the concrete beam. This arises because the slab that is on top of the concrete beam is poured with the beam and it acts together, and so you can account for that if you apply the code properly. Let's now move on to columns. Now, one thing to realize that's very important about columns is that columns will resist, of course, axial loads, but they also almost always will also be resisting some bending loads. And so there is this interaction between those two types of loads. The next thing that I want to identify here is that most columns are what we consider to be short columns. And since this is an introductory video, I will say right now we're just assuming for the time being that all of your columns are going to be short columns. You don't have to worry about second order effects and slenderness problems. And so having said that, we now can look at the code requirements for the gross steel ratio. This is denoted by rho sub g, and so the gross steel ratio needs to be greater than or equal to 1 and less than or equal to 0.08. So this is rho g minimum and this is rho g maximum. Now, I want you to also notice that this is rho g. It is not just rho. And so it is a steel ratio based on the gross cross-sectional area of the column. So you can tell that by the fact that rather than having B times D on the bottom of this ratio, we have B times H. And this steel, the gross area of steel on the top of this expression, is not just the steel in the tension zone. It is steel that is evenly distributed throughout the cross-section of the column. And we're going to see some examples of that later. But just remember, this is the total area of steel that is in the cross-section for a column. As I said before, columns will take axial load and bending. And if you want to try to get a trial column cross-section size in terms of an area, you can do that by using this formula here. This gives you the gross cross-section of the column. Notice that this is A sub g it's not for the steel as it was up in this formula. This is the gross area of steel in the column. This is the gross area of concrete, and this is our trial size, and so it needs to be greater than or equal to this formula. Now this is just going to give you an estimate. It's not going to be perfect. You might have to make some adjustments in the course of doing your design. You may find that it's either too small or too big, but it will at least get you started. We oftentimes will assume that our columns are square, but it is true, sometimes they are rectangular. But for your purposes at this point, assuming a square column is probably a decent idea. Now, the other thing that you will have in your columns, besides the steel that is along the length of the column, is you will have what are called ties in the column cross-section. And they will look very similar to stirrups that you saw in the cross-section of a beam. For whatever reason, in concrete design with columns, they tend to call them ties instead of stirrups. And so that kind of is a little bit of different jargon when you're speaking of a column. In our next slide, I'm going to show you some examples of column cross sections with longitudinal steel reinforcement and also ties in the column cross section. Now before we finish this slide, I want you to imagine you're going to design a column, and of course at some point you're going to need to calculate the maximum M sub u in the column and the maximum P sub u that is acting on the column. Those two factored loads are going to come from the same load combination. Don't try to mix these between different load combinations. They should come from the same load combination. And it might be that you have to try several different load combinations to figure out which one provides the worst pair. In any case, we're going to learn more about this as we go in our slides. But first off, we're now going to look at column cross sections and how ties might be placed in the columns. So here are some examples of some column cross sections. You can see in this one at the four corners, we're seeing the cross section of the bars that are along the length of the column. These are often called the longitudinal bars. These this square bar that goes all the way around is what we call the tie, and they are spaced along the height of the column, and they are like stirrups that we saw in reinforced concrete beams. Now, depending on how big your column is and how much load it needs to resist, you may have more longitudinal bars. You can see a lot of different examples on this page. And also, depending on the spacing of these longitudinal bars, you may have to, according to the code, add additional ties like this picture you're seeing in this middle example. Certainly, there's a variety of arrangements, but this kind of gives you an idea of how column cross sections can be reinforced. Now, I also have created a computer program for calculating what is called an interaction diagram for columns. And this program, of course, requires some input. And the resulting output, of course, kind of shows up over here in terms of numbers that you can look at. But also, the more important thing probably is this interaction diagram. And it is a plot of phi Vn versus phi Mn. And the goal is that your M sub u, comma P sub u, which is a coordinate on this graph, and perhaps it ends up right here as this red dot. This red dot does end up inside this black dashed line, and it is below this red line. If it is within this envelope, then that says that the column that was created to generate this outline or this envelope is adequate for this load combination of M sub u and P sub u. So we want our M sub u, P sub u coordinate to be inside this envelope. If it is outside this envelope, then it is not acceptable. And so this program is very, very helpful. And when you take your course in reinforced concrete design, you will learn how this envelope is generated. But suffice it to say that if you give the proper input for your reinforced concrete column, it will, this computer program will generate this graph for you. Now, the other thing that we are going to talk about is just a little bit about slabs and footings. And so I have some bullets here, and I want you to know that for slabs and footings, there is an analysis that you can do for those, and you will find that slabs and footings have bending and shear just like beams. You can design the bending capacity and find phi mn just like we did for beams. You can also calculate phi vn just like beams. Now there are some other things that have to be considered. For instance, footings have to consider something called punching shear, and this kind of has to do with the column that is sitting on the footing kind of breaking through, punching a hole through the footing. And we'll talk about that more in some of the examples that you may see later. But for now, you just realize that that's something that will come up when you get to more advanced design concepts. Now, in slabs and footings, we usually don't have shear reinforcement. And oftentimes what we do is we design the footings and the slabs thick enough so that we don't need the shear reinforcement. And usually it's more efficient to do it that way, and most people do that. The other thing is that you know, there are some minimum shear reinforcement requirements in the code, but slabs and footings are a place where there is an exception to those requirements. So you are not required to have minimum shear reinforcement. The other thing is that when we were learning about beams, we said that there were minimum and maximum, or I guess I should say minimum steel ratio requirements for beams. And those minimums do not apply to slabs and footings. However, for slabs and footings, we do have some requirements for a minimum amount of temperature and shrinkage steel. And those values are based on the gross cross-section of the slab or a footing. And this is just like when we were talking about columns. We had a gross cross-section, and we could calculate a rho g value for the gross cross-section. Here are the rho g minimum values. We need to have more, a bigger steel ratio than this if we are using steel that is less than 60 ksi. And our rho g minimum is 0.0018 for steel with a yield strength of 60 ksi. So basically the total section steel area on the gross cross section of concrete needs to be this amount, which is rho g minimum times B times H. So we can calculate this quantity and make sure that the steel we provide is greater than this value here. Now, here are a few comments. In conclusion, You are the engineer. You get to choose what the size of your beam and your column are. However, you must, after you've made your choice, make certain that the ultimate strength design or this LRFD type formula is satisfied. Our nominal factored resistance must be greater than or equal to the factored loads. That is a requirement that always must be true. Now, reinforced concrete can be challenging because there are many code requirements. We've only touched on a few of those things, so certainly remember that this is an introductory video. There are many other things to be covered or to be learned about reinforced concrete. So I hope that this introduction is helpful, and as I said, there are some other videos that will be provided to you as well.